Number 18 says, let G be a group with order P squared, where P is prime. Prove that the center cannot have order P. What's a theorem that would be related to this? A theorem in a recent chapter involving the center. GZ theorem, yeah. Again, this is a little bit of a strange theorem, but it is true. And sometimes it's useful, like in doing the problem we're about to look at here. If G is a group and Z of G is the center, then the factor group, G mod the center, if that's cyclic, then G is abelian. Again, it's kind of a strange theorem because if you think about it more, if this factor group is cyclic, then G is abelian. That would also mean if G is abelian, Z of G is equal to G. If G is abelian, its center is itself, because everything commutes with everything else, which would actually also mean the factor group is trivial. If G and Z of G are the same, then you're modding by the group itself. It's only got one coset, one element. This factor group is a trivial group. So what it's really saying is if this factor group is cyclic, it's got to be trivial. Another important way to think about this theorem is its contrapositive is also true. If G is not abelian, then this factor group is not cyclic. Another way to say that, based on what I just said a minute ago, is if the factor group is non-trivial, it can't be cyclic. Non-trivial factor groups of this form are never cyclic. Amazing. That's like weird. Like, why wouldn't there be some examples where they're cyclic? Well, this theorem and its proof proves it. How's that useful? Order G equals P squared, P is prime. The center of G cannot have order P. You're trying to prove something's not true. Sounds like a good situation for maybe using a proof by contradiction. Like the classical situation where you use a proof by contradiction is to prove square root of 2 is irrational. What does irrational mean? It means not rational. So the proof is by contradiction. Assume to the contrary that square root of 2 is rational and get a contradiction out of that. Similar kind of idea here. You're trying to prove something's not true. These things are not equal. So assume they are equal and see if you get a contradiction. By way of contradiction, assume Z of G does have order P. Evidently, if we're going to use the GZ theorem, though, we better think about the factor group. What would the order of the factor group be? Say it again. Yeah, P squared over P. Why? Well, the order of the factor group by definition is the index. Why? Because the index by definition is the number of left cosets. And Lagrange's theorem also says the index is equal to this. So this equality is definition of index. And you also could say it's the definition of the factor group as being made up of elements that are cosets. And this is Lagrange's theorem. Second sentence in Lagrange's theorem. And by assumptions, that's P squared over P, which equals P. Are we pretty close to being done? Is this a contradiction? Doesn't seem like it at face value, but claim it is a contradiction based on things we should know for the test, like the GZ theorem. Like, how does now using the GZ theorem lead to a contradiction? You have to use a little bit more than the GZ theorem. Let me add a little extra note in here. That's relevant too. We need another fact here. We need a classification fact as well, a corollary of Lagrange's theorem. How is the fact that P is prime relevant? I mean, I stated it was prime, it must be relevant. Subgroups that have to have order 1 and order P. What would that mean about elements? Elements have order 1 and order P. What would that mean about this factor group itself having order P? Any group of order P is cyclic. That was a big deal. That was a big deal last week. I made a big deal out of that. That's a corollary of Lagrange's theorem. It's a classification factor. Remember, that's one of our main purposes. One of our main goals is classifying groups. And that's a corollary of Lagrange that I highlighted, I think, last week. You should know this for true-false questions, certainly, and questions like this. Every group of prime order is isomorphic to ZP. In other words, they could have stated the corollary better. Probably a better statement of this would be to say, if G is a group of order P where P is prime, then G is isomorphic to ZP. In other words, G is cyclic. We've got a group, the factor group, having order P where P is prime. It's got to be cyclic. It's cyclic since P is prime. Therefore, by the GZ theorem, the conclusion is G is abelian. Therefore, Z of G actually equals G. So the order of ZG is P squared, because G had order P squared. That's a contradiction. We assumed the order of Z of G is P, but now we conclude that the order of Z of G is P squared. That can't happen at the same time. Contradiction. Therefore, the order of Z of G must be not equal to P. The other two options are the order of Z of G is 1 or the order of Z of G is P squared. Do we know what the true order is? Is it 1 or is it P squared? I actually do not know what the true order is. The true order of Z of G in this context for this situation is actually P squared itself. If G has order P squared or P is prime, actually the center has to also have order P squared. It's got to be all of G. In other words, G has to be abelian. That's a classification fact as well. You should know this for the test too. Classification of groups of order P squared, where P is prime. Every group of order P squared, where P is prime, is isomorphic to one of two things. All right, this could be a true-false question as well. It's either cyclic of order P squared, or it's an external direct product of two cyclic groups of order P. And since P is not relatively prime to P, these two are not isomorphic. These are two distinct isomorphism classes. But these are the two possibilities, but they are both abelian. And that's actually the next corollary is that if a group has order P squared or P is prime, G is abelian. And that would mean the center of G is all of G. These are classification things you should know. So we've classified groups of order 4. Well, groups of order 1, 2, 3, 1, 2, and 4. Say that again. We've classified groups of order 1. They're trivial. They're all isomorphic. We've classified groups of order P, where P is prime. They're all cyclic. We've classified groups of order 2P, where P is a prime bigger than 2. It's either isomorphic to Z 2P, cyclic, or DP, dihedral group of order 2P. And we also, one more case, have classified groups of order 4. That was at the beginning of chapter 8. Classification of groups of order 4. It's one of those two possibilities. Actually, that does fit the P squared case. We just classified groups of order P squared, and that fits that case as well. But here we did it a little earlier as well.